Can you smile, Layla? Layla, can you smile? Smile, little sweet cheeks. Smile, little sweet cheeks. Hi. Hi, dear. Quinny, say, calculus is awesome. Say it. Go, calculus is awesome. Can you say that? Layla, can you say it? Calculus is awesome. She did it. Can you say, I love to optimize? Say, I love to optimize. You're tired. Layla, can you smile? Can you smile? Quinny's being silly, isn't she? Quinny's being so silly. Quinny's going to make everybody seasick. Quinny, you're goofy. You are goofy. Look at Quinn. Look at Quinn. You're silly, Quinny. Okay, Modeling and Optimization, Section 4.4. Quick review questions right here. And the solutions. And the topics that we're going to be talking about today. We're talking about examples from mathematics, business and industry, economics, and we are modeling discrete phenomena with differentiable functions. This is a huge application section of calculus, and we're talking about how to optimize things. Basically, we're trying to figure out if I want to find the maximum production of an item, or if I want to figure out the minimum perimeter it would take to build a fence. Optimization basically means finding maximums and minimums in real-life situations. Here are the strategies for solving max and min problems. These 4 steps, the very first 3 steps, we all did in pre-calculus last year. The only difference now is we are now, instead of using the calculator to find these answers, we're using calculus to find these answers. So the first thing we want to do is determine what it is that we're trying to find. If we're trying to find the maximum area of the fence, then we need to come up with an area formula. If we're trying to find the maximum production of the maximum production level of an item, then we're going to have to be coming up with a production function. And so that's the very first thing, is to know what it is that you're trying to find. The step 2 is to develop that model, and this is usually the hardest part, is just coming up with the function that models that maximum or that minimum. And so, for example, area is length times width of a rectangle, but you can't have an L and a W. So we're trying to get everything down into one variable where we can then take the derivative of that. The third thing is to determine the domain of our equation. We have to determine the domain to know if we have endpoints or not to test. For example, if I'm taking a sheet of paper, which is like an 8 by 11 sheet of paper, and I'm trying to cut squares out of it, out of the corners, so that I can fold them up and make an open box, then there's certain amounts that X can't be. X can't be 7 inches because a 7 by 7 inch square wouldn't fit in an 8 by 11 inch paper. So you have to understand what your domain is before you can ever really truly find the max or the mins, because those could occur at the endpoints. And then the last thing is to find the critical points. Now this is the new part from what we did last year in calculus, where we are now using the derivative to determine max and mins instead of using the calculator and doing the second trace and then doing the max and then finding it that way. We're now going to use calculus because we now know how to find maxes and mins using the first derivative. So this is an example that I'm going to go through with you, and then later I'm going to have our friend, Mr. I never even know what his name is, but anyway, we're going to go back to him, and he's going to go through 3 examples with you, and that will be the end of this lesson. And then a lot of the rest of this section is just us going through problems, working through problems. Once you have the system down, you should be pretty good. It's now just a matter of applying it. So I'm going to go through with this example. It says a rectangle is to be inscribed under one arch of the sine curve. What is the largest area the rectangle can have and what dimensions actually give that area. So I have a picture of it on the slides, but I would like to go to an animation that I created for you. Here it is. So this is GeoGebra. This is the program I told you about that is so useful. But I've created this picture of the sine curve. You can see that it goes from 0 to pi, and that is just the top half of the sine curve, and you can see this rectangle that is inscribed inside of this sine curve. Now what we're trying to find out is, where do I have to place these edges of my curve on the sides so that the rectangle that I would create would have a maximum area. So hopefully that helps us at least understand what it is that we're trying to find. So we are going to have to be dealing with an area function, which is a length times width for a rectangle, but we just now have to get everything into x's in this case so that we can then find the derivative instead of l's and w's. So here is the solution to this. Now I'm going to go through this piece by piece with you, but what we are trying to find is the length here and the width, or the height, of this rectangle. Now, if we all agree at least on one thing, if I would just make this an arbitrary x value right here, then what that means is that the distance from the y-axis all the way to this vertex right here would be x. Now, sine is symmetrical, so that would mean that over here, this guy's width would also be x. Okay? So that leaves this piece, which is the base of the rectangle, would be a width of pi minus the two x's that we've cut out of that. So we should realize here that the base of our rectangle is pi minus 2x. So that's how we got base. The height, if I were to say that this is x here, then do we all agree that the height is the value of the function at x? So our height is f of x, and in our case, f of x is sine of x. So I have my base, pi minus 2x, times my height, sine of x, and so now I have a function that has only x's in it. And that's the whole purpose. That's step 2 of what we're trying to find. So we have step 2 done. Step 3 is to determine the endpoints. And what we should at least recognize here is that my endpoints, or my domain rather, of this function, x can't be anything bigger than pi over 2. So 0 to pi over 2 is going to be the domain of our function. The fourth step is to find the derivative, and obviously here this derivative, the derivative up here at the top, would have to entail the product rule. So we have the first times the derivative of the second plus the second times the derivative of the first, and we just have it reversed here. So this is the second part of the product rule, and this is the first part over here, the product rule. And that is then going to be used to find our critical values. So we set that derivative equal to 0, and using the calculator then, we put this into our calculator, we find out that it equals 0 at 0.71. Okay? So again, we put 0.71 on our continuum, and we realize that on the right side, or I'm sorry, the left side of 0.71, I would get a positive in my derivative, which means that my original function is increasing. And then on the right side, I put number in past 0.71, and I get a negative. So we can see that because the derivative is going from plus to minus, then our original function has a maximum there. Therefore, the area of the rectangle is a of 0.71, which is 1.12. That's the area, where the length is then 1.72, and the height is then 0.65. And I get that by putting that back into my area function up here, or setting my area function equal to, or putting 0.71 in for x, and that will give me the length and the width. of my rectangle.
Look at an example where we apply this method to solving a real-world example. Minimizing perimeter. What is the smallest possible perimeter for a rectangle whose area is 16 inches squared? And what are its dimensions? Okay, so what we know is the area is equal to 16, and the area of a rectangle is length times width. So we start off with area equals length times width, which equals 16, and therefore, in this I can solve for L and say that L is equal to 16 divided by W. Now let's go to perimeter. The perimeter, which is what we're trying to minimize, is equal to 2 times the sum of L plus W. What we need to do, though, of course, is replace or substitute the 16 divided by W for L so that we have this P in terms of just one variable, in this case W. So P would be equal to 2 times 16 over W plus W. And that would be equal to 32 over W plus 2W. And now what we need to do is take, because we want to find the maximum, or I'm sorry, the minimum perimeter, what we want to do is find the first derivative, because that's what allows us to find either a max or a min. So we take the first derivative of this. P prime is going to be equal to, off to the side here, I want to point out that this is really 32 times 1 over W, and 1 over W is just like 1 over X, and we've seen that many times, so we know that the derivative of it is negative 1 over W squared. So it's going to be, in this case, negative 32 over W squared, and then plus 2, because that's the derivative of 2W. Now we need to set this equal to 0, and then solve that for W. When we work out the mathematics of this, we will get that W is equal to plus or minus 4, but of course, but of course we don't deal with the minus because you can't have a width of negative 4. So if W is 4, then we can calculate L, remember, because we said L is equal to 16 over W. So we get that L is equal to 4. Well, what that tells us is that it's actually, the perimeter is 16, and it's really a 4 by 4 rectangle, i.e., it's a square. So that's our answer. Let's try another problem. Let's take finding an angle. We have two sides of a triangle which have length A and B, and the angle between them is theta. What value of theta will maximize the triangle's area? And the formula we're going to use for this is the hint. Area is equal to 1/2 times A times B times sine of theta. So what we're going to do is write down the area, which is 1/2 AB sine theta. And what we're trying to do here is maximize the area. So we take the derivative, the dA d theta. So we're taking the derivative of the area with respect to theta. Well, all of these are constants. A is the side of the triangle, B is the side of the triangle. So those remain as is. And now the derivative of sine theta is cosine theta. We set this equal to 0 because we want to find the critical point, the point at which it's either a max or a min. In this case, we're looking for a max. But what we know is this will be 0 when cosine theta is 0. And the angle whose cosine is 0 is pi over 2. And what that tells me then is that it's a 90-degree angle. Oh, 90-degree angle means that it's a right triangle that will maximize the area given a triangle. It's got to be a right triangle. Let's carry these ideas even further and do an example from business. We're going to design a poster, and what you know is this. You're designing a rectangular shaped poster to contain 50 square inches of printing with a 4-inch margin at the top and a 2-inch margin, I'm sorry, at the top and bottom, the 4 inches, and a 2-inch margin at each side. What overall dimensions will minimize the amount of paper used? I think it's best here if I draw a picture to help describe what we're trying to do. We've got the inside writing area of the poster. And so we have L and W. But now what we know is that we have to have a 4-inch margin on the top, a 4-inch margin on the bottom, a 2-inch margin on each side. And so the overall poster would look like this. And I know that the width is actually going to be W plus 2 plus 2, or W plus 4. And I know that the length would be plus 4 plus 4, so L plus 8. What I'm told in the information is that the area of the writing is 50 square inches. So area is L times W, which is equal to 50. And this time I will solve this for W and say that W is equal to 50 over L. Then what I know is for the whole poster, my area is the full length, which we said was L plus 8, times the full width, which is W plus 4. I want to make a substitution of 50L for W so that I have this equation just in one variable. So my area is going to be L plus 8 times 50 over L plus 4. And then I want to multiply all of that out and simplify it a little bit. And when I do that, I'm going to end up with 4L plus 400 over L plus 82. So this is the area that we want to maximize, and therefore we have to take the first derivative, that is find A prime. That's going to be 4, and here's our famous 1 over L times 400, so it's going to be minus 400 over L squared. And 82, of course, turns out to be 0. We have the first derivative now. A prime is equal to 4 minus 400 over L squared, and we need to set that equal to 0 and solve for L in order to find the minimum amount of paper. So we set it equal to 0, and then we solve for L. When we do that and work it all out, L works out to be equal to 10. Now, if L is equal to 10, we know that we actually have to add 8 to that. So the poster's is going to be 18 inches tall. And now in terms of W, remember that W is equal to 50 divided by L, which means the width inside of the writing is 5. And that makes sense because 5 times 10, the length, would give us the 50 inches of writing. But remember that we've got to add 4 to W. So W is 5, but the poster itself is 9 inches wide. So it's 18 inches tall and 9 inches wide. Now we're going to try an example from